This video aims to explain magnetic flux, Lenz's law, as well as Newman's equation. We are assuming that you have seen all of the demonstration listed out on page 4. And from those demonstrations, we come up with 3 conclusions. Firstly, that an EMF, or electromotive force, which pushes charges along a wire, is produced whenever the wire cuts across lines of magnetic field. Observation number 2, also listed on page 5, is that an induced current is created when there is a complete circuit and we have a changing magnetic field. So the classic demonstration that we see this in is when we had a solenoid and we had a magnet and we pushed the magnet into the solenoid. Previously there was no magnetic field, and as you bring the magnet closer and closer, then the magnetic field changes. The third observation is that the faster the movements, the larger the induced effects. But we must consider, does this explain all of the scenarios that we see? If you scroll down page 5, you'll notice that there is a new scenario where there is a pair of magnets, a north and a south pole, arranged where north is on the top and south is on the bottom, and there is a loop inside the magnetic field. The only thing that we've done to the loop is to stretch it into a larger loop. At this moment, it is at the positions A, B, C, and D, but the two sides, AB, get stretched towards A dash B dash, and the sides D, C get stretched to D dash C dash. If you're watching this video, it will be really awesome if you can pause it now to see if you can figure out, does the stretching of the wires produce a pair of EMFs that might perhaps force a current around the loop? Pause the video now, you should have a go, and if you don't remember how to do this, pretend that there's only a single wire at AB, and just like how we started the unit off with a little man pulling the wire through a magnetic field, have a go. I'm assuming that you've had a go at this for yourself, and now let's have a look at how to complete this problem. Here, the first thing you need to consider is the direction of the magnetic field, and we know that magnetic field comes out of the north and into the south, so I'm going to label that B with a hat on the side. I should draw lots of field lines across all of the magnet, but because my loop is there, I don't want to put it into the diagram. It's going to be really hard to see what's going on. Now that I've got my magnetic field line, the next thing I need to consider is what's happening to each side. I'm going to consider side AB first. So at the side AB, if the wire is stretched to A dash B dash, then that means that the charges have moved to the right. And if the charges have moved to the right, we can safely say that with our right hand open palm rule, this is the direction in which our thumb should be pointing. The reason being that the charges actually moved to the right. If we point our thumb in that direction, then our fingers must follow our field lines, and our fingers are pointing down the page. If you hold your right hand open palm in those directions, then your palm is now facing, there's only one possibility, your palm must be facing A, or alternatively A dash. So if that's the case, then we know that then positive charges must have moved over here to the A or A dash side during the stretch. Similarly then, we can use that same idea on the side DC. If the wire from DC has moved from DC to D dash C dash, then we know that our thumb needs to point now to the left on that side. With our fingers pointing down, our palm would face C. That means our positive charges are going to be over here. Since I have a displacement of charge that moves like so, we can assume that the charges moved in these directions. And if you see the arrows that I've drawn to illustrate the movement of the positive charges, it does actually form a pair of EMFs that drive current around a loop. So the answer to this question is yes, it does allow for current to move around the loop, And since the current moves from D to C or C dash, then it will push charges further along on the sides that actually don't have any induced effects, and a current is established like so, as I've illustrated here in red. If we consider the actual loop, and this is a very important question, we have stretched a loop inside a magnetic field. We haven't stretched it outside the magnetic field. It is still within the magnetic field during the stretch. But somehow I can generate a current. And if we think about it, is it fair to say that the loop was subjected to, let's say, a changing magnetic field? Because that was the conclusion that we drew from up here from all of our demonstrations. Well, did the magnet change in strength? And the answer is no, it didn't. In fact, it didn't change in strength, so there must be a different consideration that we must think about. In fact, since the answer to this question is no, the magnetic field is the same, there has to be a new explanation for why it is that we can actually induce a current in wires within a magnetic field. So let's have a look at how we can consider a new explanation. Remember, in science, if one explanation doesn't work, there must be another. And here we bring up the idea of magnetic flux. Magnetic flux is a really cool quantity that allows us to consider the induced effects that occur when we have a loop or a coil of wire that is actually able to experience some induced currents. Magnetic flux, at its purest form, is defined as the product of the mutually perpendicular components of the magnetic field and the loop area. Proverbially, it is also really just, I guess, the area in which the magnetic field lines can cross at any given time. It's probably easiest to explain with a diagram here on page 6. I've got a rotating loop. It is currently at an angle theta to the vertical. I'm going to highlight the theta in this yellow highlighting. I need you to switch on your imagination so that in the room that you're in, the ceiling is the North Pole and the floor is the South Pole. Your imagination should also have the idea that you can actually see magnetic field lines coming out of the north into the south, just like this green highlighting that I've used. As we have this in our minds, we now need to imagine a loop. Some students actually require a physical loop, like a piece of paper, but we're just going to try to use your left hand because that's what you'll have in the exam. So I'm going to ask you to open out your left hand so that your palm is nice and open and your fingers are nice and straight with respect to the palm. And then if you move your left hand as if you're about to dab, it'll be at the angle as illustrated on page 6 at about theta. I now would like you to rotate that back up to the vertical so that your fingers point to the ceiling and your elbow points to the ground. In this position, if you're thinking about your palm as the loop, hopefully you can see that the magnetic field lines that are coming out of the ceiling towards the ground is actually not going to cut through the area of the loop because the effective area that is seen by the magnetic field is actually 0. It might help for you to imagine that the magnetic fields are kind of like skewers or like an Indiana Jones movie where there's like arrows shooting down from the ceiling. In this position, your palm would be really safe, so no flux. But if you rotated your hand to, let's say, to the horizontal now, you'll notice that all of your palm is open to the magnetic field lines, to be able to point through your loop, okay, or effectively the area of the loop. And because when your arm is in this orientation at theta equals to 90, you have the maximum area, this would be the maximum flux position. Really cool thing about this is that when you have it rotated at the angle theta, the effective area that is actually seen by the magnetic field is actually the shaded area down here that I'm shading in red. But more particularly, we know that we also have this really cool idea of being able to calculate the effective area with respect to the angle. So let's do that now. I'm just going to draw a darker line on the side of the loop that's actually facing you. And at this particular moment, if I imagine that I've got my eyes here looking, then effectively what I see is that I can see the edge of the loop that's orientated at this sort of angle. It is currently at an angle theta to the vertical, just kept exactly the same as the diagram. But if we have a look now, the effective area that is actually seen, that little area here, the shaded area, which I think I should label with a name so we don't get confused. Let's call this L dash, is this down here. Yeah. And if the side of the loop that is rotating, let's call that L. This is L. Then the question becomes, is there a relationship between L and L dash and theta? And hopefully for those of you that love triangles, you should see that, yeah, there is actually, because if you drop a vertical line down, the two dotted lines are parallel, and so therefore this angle here must be theta because of the alternating angles a congruent rule, or the Z rule. And if that's true, then we can use one of our trigonometric function, which is sine theta equals to opposite over hypotenuse. And for us, our opposite side is L dash, our hypotenuse is L, and so sine theta is equal to L dash on L. We can also have a look at what this really means, because now I know that L dash by itself is really just L sine theta. You might be going, well, that's really cool, but why is this important? Well, I'm going to label the other parts of the loop. Now, I'm going to try to illustrate the loop as if it is not square. So I've got a length and a width, which might be different values. And so as we rotate the loop, the width of the effective area doesn't change. The only thing that's changing is L dash as we cycle through different angles of theta. And if I now think about the effective area of the loop, so the effective area is always equal to L dash times the width. That would be the shaded area down the bottom that we see. So this is the shaded area that we've got. But we know that L dash is actually L sine theta times W. Actually, we've actually got LW sine theta. Well, we also know LW is something else. L times W is actually the area of the loop itself. So the effective area is always the area of the loop multiplied by the sine of the angle between the loop and the magnetic field lines. Yeah. So this is really interesting. And particularly we're going to use the idea of flux, because if we go back to our previous page where this whole thing started, where we had a loop that we stretched and we found out that there was current traveling around the loop, we realized that, hang on a minute, there's no changing magnetic field, but if you stretch a loop like this, there is a change in magnetic flux. Because if you think about the field lines coming down from the North Pole to the south, if you stretch the loop to a bigger area, there's a larger area for the magnetic field lines to actually travel through or to stab or skewer. So the flux, the magnetic flux, must have increased, and that would explain why there was an induced current here. So if we come back down to the bottom here, this derivation on the right we'll use later on. It's very useful for our generator formula, but the units, because this is a new quantity, the units are actually named after a famous scientist with the last name Weber, and the actual symbol for it is a capital W because it's named after a man who died and was famous. But the really cool things that we can consider now about the induced current that can happen, under which conditions they could occur, there are, I guess, 4 ways, and they're listed out here in the dot points. We can change the relevant area of the loop. We can change the strength of the magnetic field. We can change the direction of the magnetic field, so the second and the third dot points we did in the demonstration, or any of the combinations of the above. So the magnitudes of the induced effects is directly related to the rate at which the magnetic flux changes. So if the flux changes are fast, then the induced effects will be very large. Just like how when we put the magnet in to the solenoid very quickly, we saw a much larger effect. So magnetic flux actually explains, I guess, why is it that we actually have a current? Then Lenz's law, which is on page 7, actually explains the direction that the induced current occurs. So magnetic flux, that idea, and Lenz's law actually goes together because magnetic flux explains why does the current happen, and Lenz's law says something about the direction. We're going to pause here. You might want to reflect on what you've learned on magnetic flux. If you're ready to talk about Lenz's law, continue on in the video. I'm assuming that you've had a quick read of Lenz's law, and in the crux of it, Lenz's law is really about the object that is going to have an induced current trying to generate the induced current such that it opposes the change in flux that caused it in the first place. So you need to imagine that the coil of wire or the loops that are going to have a current traveling through them, they are literally really stubborn objects that don't like to change. So they really just want to go back to the status quo. And when changes occur, they want to induce a current that would kind of counter out what change you did to bring it back to its original state, or try to at the very least. For those of you that do chemistry, there are very similar ideas with Le Chatelier's principle when we talk about equilibrium, but this is something slightly different. So cognitively, Lenz's law is just a little bit harder, but there are a few simple rules that we follow to apply it. I'm going to explain 2 ways to do Lenz's law, but first of all, I'm going to do it from first principles because it's a method that will always work. From now on, I will never talk about changing magnetic field. We are always going to be talking about magnetic flux and how it changes. So first of all, rule 1, we need to think about how the flux has changed, or I like to call this step, what the flux. And if you think of that, then in this scenario that we've got on the page for Lenz's law on page 7, you will see that there is a magnet that is going in to the solenoid. Yeah, the solenoid is connected to a galvanometer as indicated by that little circular thing with a G. A galvanometer, remember, is an ammeter that indicates current flow in both directions with a needle. So if I've got a magnet that is coming into the coil, and it says it enters, okay, so that's where the clue comes from, it's entering. That means that the magnetic flux must be getting stronger. And we use the word increasing to describe that because it's getting stronger. It would be increasing. If it's increasing, the next thing that we need to use to describe it, still the same rule, talking about the magnetic flux changes, is the direction. The direction of the magnetic field comes from the direction of what's happening with the magnet. So you can see those arrows there, they're pointing upwards. That's why this is increasing up. That's step number 1. Think about the changes in the magnetic flux. Step number 2 is actually to think about, well, what is the induced current going to do in the coil to try to resist the change? So you need to imagine this now. Previously, let's imagine the extreme case, there was no magnet. All of a sudden, there's this magnet that's zooming in, and I've got an increasing up flux. So what's the coil going to try to do? Well, it's going to try to resist it. So if there's an increasing up flux, it would then try to create a flux that's going to try to cancel this out. If it's going to try to cancel out something, first of all, it has to create an increasing amount of something. So it'll be increasing all the time, by the way, in step 2. But the direction is important. So if I got increasing up as the change, then to cancel it out, there must be some downward magnetic field to cancel it out. So this will be increasing down. So if the field lines are going opposite directions, they might cancel. And if it's increasing down, then what you should do is illustrate what this looks like. So I'm going to do this in a blue colored pen. So that means that the field lines that are coming out of the solenoid needs to look like this. And now you need to, for the step 3, you need to think about and this is B and G, sorry. For step 3, you need to think about what current would actually produce this particular type of flux. So that blue colored lines that I've drawn there. You need to remember back to the original unit when we did magnetism, and remember that solenoids actually behave like bar magnets because there's a current traveling through them. If you use a right-hand grip rule, you should be able to figure out that the current, which I will do in orange, is actually flowing, in pink, is actually flowing this way. Yep, so use your right-hand grip rule to convince yourself that inside the solenoid, if I need the field lines to be pointing down in the direction of those blue arrows, then the current must be flowing like so. And if you follow the wires around, they actually flow downwards through the galvanometer. And so this is I induced. So I've got a magnetic flux that's induced, and I've got a current that's induced. This is the basic fundamental principles of how to use Lenz's law to figure out the direction of the magnetic field that's induced, as well as the current that is induced. This is a skill that you'll need to learn. Now, this is a first principle method. There is another method to do this particular type of problem, particularly when there is a pole that comes very close to a solenoid. There is a faster method, but this particular method that I'm going to teach you doesn't actually work all the time because not every scenario has a magnetic pole like a permanent magnet coming towards a solenoid. There will be other scenarios later on where you have a loop that's being stretched, or down here at page 8 on the left hand side, you've got a loop that's rotating in the magnetic field. So, but the second technique is fast. So I'm going to rub all of this out. So hopefully you've copied it down, but I'm going to rub all of this out and we're going to reimagine what's happening. I'm going to use the same ideas though. The idea is Lenz's law. It's going to try to resist the change. At the beginning, the solenoid is by itself and the North Pole is coming closer and closer to the solenoid. If the North Pole is coming closer and closer to the solenoid and the solenoid is trying to oppose the change, it's going, no, don't come any closer. If it's trying to go, no, don't come any closer, it's going to actually create a particular pole on one side of this magnet, right? It's going to try to repel it, yeah, because it's trying to oppose the change. A magnet's coming close to it, it's like, no, I want to keep the same, I just want to be all alone. So then this would make sense that down here, to repel a North Pole that's coming closer and closer, you would try to have a North Pole down here. And if a North Pole is down there, then solenoids behave like a bar magnet, then a South Pole would be there. And if this is the case, then we know that in magnetic field lines, North Poles have magnetic field lines coming out of the North and into the South, like so. Out of the North, into the South, like so. So notice that I've actually drawn my magnetic field induced just by thinking about trying to repel a pole that's coming close to me. And once I get the induced magnetic field or the induced flux, now I need to think about what current would produce that particular field that's in blue. And the only current that would do so is the one that's going this way. Once again, you have to use your right hand grip rule, okay? But you would also get the induced current flowing downwards through the galvanometer on the outside. Remember, this technique really only works for magnets going into the solenoid. So I would love for you to have a go at these exercises that are down here at the bottom of page 7 and also at the top of page 8. Please give these a really good go. And I'm going to have the answers in the content library so you can have a look and check if they get those right. In the next video, I'll explain Newman's equation.